Welcome once again. I am starting another topic 1.2, and it is starting with the application of diode. And this is rectifier. It is diode as a rectifier, and this rectifier actually it is used to rectify the unwanted part in the input signal. So we know that the AC that we receive at our home, it is sinusoidal, and it is of this kind of nature. So the device which works on DC will not work on such type of AC signal. So we need to convert this AC into DC for that device to work normally, because when we give such type of signal to a DC device like mobile or any device that works on DC, so that will damage, because this positive pulse will try to push current into the device, and this negative pulse will try to fetch the current from the device. So this actually, when negative pulse will come, device will damage. So to protect the device, we have to avoid the negative pulse. So this application can be done by using rectifier, because rectifier rectifies the negative pulse. It rectifies the AC component from the input signal, and it gives DC at the output. And diode can be used as rectifier. It is the important device for rectification purpose, because the diode is a unidirectional device. It flows current only in forward direction. It allows current to pass through it only in forward direction from anode to cathode. It never allows current to enter from cathode side unless it is in normal condition. When it gets breakdown, it allows current in reverse direction also, but that is the extreme case. We will only use the diode in normal condition without going under breakdown. So in that case, diode only pass current in forward direction, and it blocks the current in reverse direction. So this one way nature of diode rectifies the negative pulse, because when positive pulse comes, it passes the current into the load. So the diode will permit that direction of current, and this, when the negative pulse will come, the negative pulse will try to take the current from the load towards itself. It will try to fetch the current from the load, and that reverse direction of current will be blocked by diode itself. So the load will be protected. So this is the application of diode as a rectifier. So before starting, we must know some basic fundamentals about the signal, AC signal. This is a sinusoidal signal, and if you want to represent this signal using mathematical form or mathematical equation, we can represent this by this equation: V equals to Vm sin theta. In more detail, we can express the same signal using this formula: V equals to Vm sin omega t plus phi. So this is the actual detail form of mathematical expression, and this represents this equation, this type of waveform. This Vm is the peak of this waveform. This is a height of positive pulse or negative pulse from the horizontal line, that is at 0. So this is the peak here, and this peak is appearing at pi by 2. This is pi, this is 0, and between this 0 and pi there is pi by 2, and at pi by 2 the height of the signal is Vm. So this is maximum amplitude of the signal. Here also at pi, between pi and 2 pi, it is 3 pi by 2. At this we get minus Vm, but the difference is the height is Vm, magnitude is Vm. So this Vm will give the magnitude of signal. This sign will show the nature of signal, because the nature is sinusoidal. And this bracket term, in the bracket term we have omega. It will express the frequency. Actually we can express the omega as 2 pi f So this f is actually frequency of this signal. We can measure the signal from 0 to 2 pi, this complete cycle of signal, and the time required to complete the cycle is known as time period of the signal. And this time period, it is represented by capital T. Here it is written, this signal, the time required to complete one cycle of signal, it is given by periodic time T. And frequency can be found out by T as this equation, frequency equals to 1 by T. When you take the inverse of time required to complete the cycle, if you take the inverse of it, you will get frequency. So the frequency can be obtained by inverting the time. So this 2 pi f is actually omega. So this is actually here the small t, it represents the domain in which you are working, you are expressing the signal. We are actually expressing the signal in time domain. Here t is written, this is actually in time domain. So we are looking the signal in time domain. So this t is actually representing the domain of representation, and this phi is actually phase, because here the signal is starting from 0, from origin itself the phase will be 0. But if the signal is starting after some time, if it is starting at pi, then that will be called as delayed signal or a lagging signal, and that in that case the phase will change. So we have to only work on the amplitude and the nature. So if we are not about to work on this, so we will remove this by theta. So our signal will reduce to Vm sin theta. But in this case our domain will also change from t to theta, but that doesn't matter. So you must know that this Vm is the peak amplitude of signal, and sine is the nature of signal, and theta will show the angle. Theta will show the angle from 0, pi or 2 pi. This is the value of theta. So theta will, at this point theta is 0, at this point theta is pi by 2, at this point theta is pi, at this point theta is 2 pi. So this is actually domain here. So if you are clear with this topic, this is the mathematical representation of signal, sinusoidal signal that we receive. This is the maximum peak Vm, and from 0 to 2 pi it is complete cycle, and time required to complete the cycle is capital T, and inverse of this T is pi. Now coming to the rectifier, there are two types of rectifier, half wave rectifier and full wave rectifier. The rectifier that only passes half wave from input to output. Half wave means this is complete cycle, complete wave. Only the rectifier which only passes the positive pulse and suppresses the negative pulse, that will be called as half wave rectifier. And full wave rectifier, it rectifies both pulse, it passes the positive pulse and it also passes negative pulse, but by converting this negative pulse into positive pulse. So it is called as full wave rectifier. In half wave rectifier we get only half wave at the output, and in full wave rectifier we get full wave at the output, but negative pulse is converted into positive pulse. So this task of converting full wave means full wave rectifier is of two types: center tap full wave rectifier and bridge rectifier. So we will study one by one. This is circuit of half rectifier. In this we require only single diode, because a single diode, the nature of diode is a unidirectional device. It is a unidirectional device. It passes current only in forward direction, that is from anode to cathode. It passes current from left to right only. So in this circuit diagram, this Vi is the input voltage of secondary, this Rs is the internal resistance or internal impedance of this secondary winding, this Rf is the forward resistance of diode, and RL is the load resistance, and output voltage across load is VO. This current is the current in this loop. The circuit must be grounded at this side to work normally. This is transformer, and these two lines are actually core of the transformer. These two vertical lines represent the core of transformer, and this is primary winding of transformer, and this is AC input signal that we have at our homes. So when we connect AC signal here, the AC will have positive and negative pulse. So when positive pulse will come, the upper of this primary becomes positive and lower become negative, so current will flow from positive to negative like this. So in this case this secondary is mutually coupled with the primary, so the upper part of it will become positive. So in positive half cycle of input, the upper part of the secondary will become positive and lower will become negative. In this case, the current will flow from positive to negative, and this current is going from left to right through the diode, so it will permit current to pass through it. Diode will allow current to pass through it because current is entering from its anode side. So this current will flow like this. And in second half cycle, of the input cycle, lower part of primary will become positive and upper will become negative. In this case, the lower part of secondary will become positive and upper will become negative. In this case, the current will try to flow from positive to negative, but in this case the current is trying to enter the diode from cathode side, and that will not be possible because diode never allows current to to enter through cathode side. So when in negative cycle, the lower of secondary is positive, and in this case the current will never enter from the cathode of diode, so negative cycle will be removed. So if you can see the graph of it, the positive half cycle will be available at the output side as it is, because the diode has opened the gate for current to pass through it, so no current will be blocked here, and the positive cycle will be passed from the secondary to the load as it is. So you will get the output like this. But when negative cycle will come, the diode will block it, so you will get 0 at the output side. That cycle will not appear at the output side, so you will get 0. When second cycle, positive cycle will come, and you will get that at the output, and when negative cycle again will come, it will be blocked by diode. This is the working of half wave rectifier. So when you are asked to explain the working of this half wave rectifier, you have to explain two cases. Case 1 will be positive half cycle and case 2 will be negative half cycle. So in positive half cycle, you have to explain that the current will rotate like this from the top of secondary to diode, from diode to RL, and from RL to the lower side of secondary. And in this case, the diode will be forward bias because positive is connected to anode, so diode will be forward bias. And in negative half cycle, that will be case 2. You have to explain to both cases, positive half cycle and negative half cycle. In negative half cycle, you have to explain that the lower of secondary will be positive, and the diode will become reverse bias because positive is connected to cathode of it, and because of this no current will flow in the secondary side, the secondary loop. And you have to explain this with the help of circuit diagram and this waveform. If you got this, then we have to bring a relation between current and voltage in this output loop. So for that we have to apply KVL here. So this will be the result of KVL. So I am bringing this figure down. So applying KVL in this circuit. So we have to first know the rule of KVL. So we can apply KVL either in clockwise direction or it can be in anti-clockwise direction. Both is possible and result will be same for both. Second rule is that when we apply KVL, we will reach RF. So this is actually internal resistance of diode, forward resistance of diode. So the voltage drop at RF will be like this. The left will be positive and right will be negative because current is going from left to right. So when current enters the resistance, it gives positive sign to it, and when it leaves the resistance, it gives negative sign. So when a current enters from left to right, the sign will be plus and then minus. So in this KVL, in this closed loop, when we apply KVL from KVL, and when we reach RF, we will get plus sign first and then minus sign. So either we can take this plus sign in KVL as positive, or we can take this as negative. If we take positive, then we have to keep the rule same throughout the loop. If we are taking the first plus as positive, then we have to also take the first plus here as positive. So there will be a drop at RF, there will be a drop at RL and RS, but there will be some rise here because when positive cycle will come, the upper side of primary will become positive, and same is the case here, the upper of secondary will become positive. So if upper of secondary become positive, the current will leave from this, and if it is positive, then from down to top, we will see the rise in voltage. So we will see a rise in voltage at the secondary, and we'll see a drop at RS. This is actually internal resistance. It is not shown here with a symbol. Actually it is internal resistance of this winding. So we have to imagine a resistor symbol here, of which this value is shown here, RS. So this rise will be there. We'll get a rise here, and we'll get a drop at RS, then we'll get a drop at RF. Drop means plus and then minus, and we'll get a drop at RL, plus minus, and we'll get a rise here, like this, minus and then plus. Minus to plus is rise. So if either we take drop as positive, then we have to take rise as negative. But here I have taken rise as positive, so we have to take drop as negative, because this is the rule of KVL. Total rises in the closed loop should be equal to total drops in the closed loop. Or if you take all the drops on left hand side of equation of equal sign, then if rise is given positive sign, then drop should be with negative sign. If rise is given negative sign, then all the drops should have positive signs. So here I have taken positive for rise, so there will be a rise in voltage VI, it is positive. Then there will be a drop at RS, and drop will be a voltage. Drop will be of voltage drop. So voltage is given as current into resistance, Ohm's law. So current is common throughout the loop. I is current flowing through the loop, so the drop will be I into RS. At this RS, the voltage drop will be I into RS, current into resistance. And at this resistor RF, the drop will be I into RF, current into resistance, because voltage is given as I, current into resistance, Ohm's law, by using Ohm's law. And at RL, again the voltage drop will be I into RF. So this will be plus VI, then minus I into RS, then minus I into RF, and minus I into RL. This is KVL. So I am explaining this first time. From next time onwards, I will not give too much time on this applying KVL. So the next step is the current I is constant in these three terms. So I am taking this current outward common, and this will become like this. And if I take I on left hand side, so you will get like this, VI divided by the whole bracket. And we know that this VI is the sinusoidal signal at the input of a rectifier. The rectifier is here, and at the input of rectifier we have AC signal, complete sine signal. So sine signal can be represented by Vm sine theta, and I can be written as Im sine theta. The current is also sinusoidal if voltage is sinusoidal, because the current will follow the nature of voltage because of Ohm's law. So I will be equals to Im sine theta, Vi will be equals to Vm sine theta. So there is no need of this. Vi will be equals to Vm sine theta, and divided by this the same terms Rs, Rf, and Rl, some of these. So sine theta will get cancelled from both sides, so you will get this relation Im equals to Vm divided by this resistances. So going to this again, this Rs is the internal resistance of the winding. Generally we name it by inductive reactance XL, but here I am using this Rs as secondary resistance, internal resistance of this winding. And Rf is the forward resistance of diode, which is very less as compared to RL. This Rs is also very less as compared to RL. So wherever we need, we will neglect this Rs and Rf in comparison with RL, because the value of Rs plus Rf together is very less as compared to RL. So we can neglect this Rs Rf in comparison with RL. So if it will be given in question or numerical, the value of Rs Rf, then we will take those values. But if it is not given, then we can neglect these two values. So we will see in numerical. So firstly we will find the average output voltage. Average output voltage can be called as DC output voltage, VDC. So average output voltage is same as the DC output voltage, the direct voltage. This can be found out by taking the average of all the values of voltage, by taking all the values of voltage from zero, from its start to the end of cycle, complete cycle. So we know that this complete cycle is sinusoidal, and it starts from 0 and it ends at 2 pi. So we have to define this term first. So I brought this figure here to explain the things. It is the output of half a rectifier. It is actually pulsating from 0 to pi, and it is off from pi to 2 pi. So we can define this mathematically. This is sine nature, so the voltage will be written like this: Vm sine theta. This is the expression of this waveform up to 0 to pi, from 0 to 2 pi, from 0 to pi. So the nature will be Vm sine theta for 0 to pi for this angle theta, and from pi to 2 pi the value is 0. So this equation is actually mathematical representation of the output of half wave rectifier. So if you want to take the average of it, we have to add all the values from 0 to 2 pi, and because this is continuous set of values, so we can add only by integration. So we have to integrate from 0 to 2 pi to add all the values from 0 to 2 pi, and this should be divided by 2 pi, because whenever we take the average, we add all the values and divide it by total number of values. So we have to divide total values. I can write this as, so I did this slight change. In this I have integrated the VO, output voltage VO, from 0 to 2 pi. So this integration will add all the values of VO from 0 to 2 pi, means from this point to this point it will add all the values, and dividing this equation, this addition, we have to divide by 2 pi. 2 pi is the total number of values, total number set of values here. So we have added all the values from 0 to 2 pi. We have to divide it by 2 pi. This will give average of output voltage, that is VDC. So I have taken 1 upon 2 pi on one side, and this VO, we have already defined this VO here. This is output voltage equation. So this equation has two limits, from 0 to pi and from pi to 2 pi, because the value of VO, it changes for different limits. So we have to split the integration in two parts. First part of integration will range from 0 to pi, and for that 0 to pi the value will become Vm sine theta. So we have to put Vm sine theta here, and for range from pi to 2 pi we have to put 0 here, because the value is 0. So the integration will remain only for this part, because whatever we multiply 0, that will become 0. So this whole integration part will become 0. Only the left part of this integration will remain, that will become Vm sine theta. We have to put VO as Vm sine theta here, and in this equation Vm is the peak value of voltage, and that is constant for the whole waveform. If Vm, if the value of Vm say is 5 volt here, then it will remain same here 5 volt, it will remain same here 5 volt. So throughout the waveform the voltage Vm will remain same, so Vm will be constant, so it has to be taken out of the integration. So I have taken this out from the integration, and the integration will remain like this: 0 to pi sine theta, and we know that the integration of sine theta, it is minus cos theta, and with the range from 0 to pi, and upper limit is pi. So first we'll put upper limit, but before that I have taken this minus sign outside to make it more simple. So when I take minus sign outside, it will remain as cos theta. So I have to write one expression. So here I have taken minus sign here outside, so minus sign is out here, and first we will put upper limit, so it will become cos pi minus lower limit cos 0, cos pi minus cos 0, and we know that the cos pi is minus 1 and cos 0 is 1. So cos pi is actually minus 1, the value of cos pi is minus 1, and the value of cos 0 is 1, so it will become minus 1 minus 1, so it will become minus 2, and this minus sign within this bracket will cancel with this minus sign, so result will become positive, so this 2 will get cancelled with this 2, so result is Vm by 2. So we have to learn this expression by heart, that VDC for half a rectifier is Vm by pi. We have to remember to write volts as unit here. So wherever we write voltage equals to some value, the unit should become volts. So we have to solve now DC output current, and the nature of derivation will remain same, because we have voltage in this pattern, so current will also follow the nature of voltage. If voltage will increase, or voltage will have a nature of sine wave from 0 to pi, the current will also have nature of this sine wave. And if voltage is 0 from pi to 2 pi, the current will also remain 0 for this range. So this equation will remain same for current, the nature of equation will remain same. It will become I equals to Im sin theta. This sinusoidal nature of current will remain for 0 to pi, and current will become 0 because voltage is 0 for range pi to 2 pi. So when we take the average of this current, I have to take integration from 0 to 2 pi into I d theta. I am changing this equation again, so I have changed it. It is now ratio of adding all values divided by total number of values. I have added all values of current from range 0 to 2 pi divided by the total number of values 2 pi. So here 2 pi is taken on one side, and here is the integration from 0 to 2 pi for current I. Here case will remain same, because the current has two values, Im sin theta for one range and 0 for another range. So integration will become in two parts. The first part will range from 0 to pi, this range, and for that the value of current will become Im sin theta, and the second integration will range from remaining part from pi to 2 pi, and the value of current will become 0 for the second part. So only the first part will remain for the derivation. This will become 0 because the value of current is 0 for this range pi to 2 pi. So integration will remain like this, 0 to pi the first part, and the value of current is Im sin theta. So I am putting here Im sin theta. Now this Im, because it is a constant value, the peak value will remain constant for complete waveform. So this as this is constant, I have to take it outside of integration, and the integration of sin theta, it is minus cos theta again, and this minus sign is taken outside. Here the upper limit is substituted cos pi, minus lower limit is cos 0. Again the cos pi is minus 1, cos 0 is 1, as we have did here, minus 1 minus 1. Here this will remain same as that, minus 1 minus 1, and this is minus 2, and minus will get cancelled, this 2 will get cancelled, and the result will become IDC equals to Im by pi. It is same as this VDC equals to Vm by pi. This is Im by pi, but we have to write in the unit of it, ampere. Wherever we write some value of current, we have to write its unit also. This is accurate value of DC, so just we have to start it from this relation, IDC equals to Im by pi. Here Im, we have already found this relation, Im equals to Vm upon Rs plus Rf plus RL. On this side, this is the relation, Im equals to Vm upon addition of resistances. So we can put this Im equals to Vm upon this equation in this relation, IDC equals to Im by pi. Im can be substituted as Vm upon these resistances. So this bracket is taken on left hand side, IDC into this bracket equals to Vm upon the pi will remain as it is. When we open the bracket, we can multiply this IDC by Rs separately, then can be multiplied with Rf separately, then can be multiplied with RL, but we have to multiply this with RL, because this gives actually VDC equals to IDC into RL, this is Ohm's law. So just I am multiplying IDC with RL, and IDC with the sum of these two resistances will remain as it is. This IDC into RL is actually equal to VDC. So when I put VDC here, it can be taken on left hand side, and remaining things IDC into this bracket will go on right hand side. So you can see this equation it has changed from this previous equation. I can copy this equation to compare it with this equation. This was the previous equation. This is equation which has this extra term minus IDC into RS plus RF. If you see this is actually a drop. IDC into RS is the drop at our resistance RS. IDC into RF is the drop at resistance RF. So if the value of resistance is given to you RS, then the drop will exist there. So we have to consider that drop in this equation. If the value of resistance RS and RF is not given in question, then we have to take these values as 0. If you put 0, then relation will become same as this relation. So I can say that this is the ideal relation, this is the practical relation. In practical we have a finite value of RS and RF, but in ideal case we have ideal impedance as with resistance RS is equal to 0. Ideally the resistance of secondary is 0. Ideally the forward resistance is also 0, but practically they have finite values. So I can say this is accurate or practical value of VDC, and this is ideal value. This is practical value and this is ideal value of VDC. Now coming to RMS. RMS is actually root mean square. It has three operation in this value. First we have to take a square of the current, because it is of current. So we have to take a square of current, then we have to take its mean, then we have to take its root, then we will get RMS of. So you can see this equation. In this I have squared the current because it is RMS of current, IRMS. So we have to square the current first, then we have to take this, the average of it, mean of it. Mean means adding all values divided by total number of values, 0 to 2 pi. This is complete range of current for one cycle, and dividing it by 2 pi. This is actually mean, then the root of it. So it will be root mean square. And now I can take this 2 pi out of this root, and I can express the root as to the power 1 by 2. Bracket to the power 1 by 2 is actually root. So for easiness I have taken this power 1 by 2. Otherwise I could have taken root here. So now this range, remember this range is actually 0 for current, because current never flows in the range pi to 2 pi for half a rectifier. It will only flow in first half cycle. It will remain 0 for second half cycle. So this will become 0 here. And the first part will remain as it is, and the value of current we have already known that it is actually Im sin theta. So I square will become Im sin theta, I will become Im sin theta, and square of it will become Im square sin square theta. So this Im is actually constant, so I have to take it out of the integration. So when it will come out of the integration, it will remain within the root. It will remain within the root. So this 2 pi is again taken inside the root. So this should be taken. This should remain inside the root. I will do it. So you can see I did this correction. Now coming from start also again, this 1 upon 2 pi will remain within the root, and this range will be splitted in two ranges from 0 to 2 pi and pi to 2 pi, and this will become 0 here. And this I square, actually I is Im sin theta, so it will be Im sin theta whole square. That will become Im square sin square theta. So this Im square is constant, so it will be taken out of the integration side, and again this sin square theta, integration of it will be it is not possible unless you remove the square sign here. So the expansion of sin square theta is actually equal to 1 minus cos 2 theta by 2. This is the expansion of sin square theta, because direct integration of sin square theta is not possible. So we have to use this equivalent of it, 1 minus cos 2 theta by 2. So now this 2 from this side will be taken out. This will become 4, and this 1 minus cos 2 theta we'll have this minus sign in between, so integration will become in two part. First integration will be of this 1 with respect to d theta, and another integration will be of this cos 2 theta with respect to d theta. So this will be in bracket, and this im square by 2 pi will remain outside the bracket, and integration of 1 where limit will remain same for both of these two, so it will be from 0 to 2 pi 1 d theta, and integration of 1 with respect to theta is theta, with respect to d theta is theta, and upper limit pi, lower limit 0, minus cos 2 theta, integration of it will be sin 2 theta by 2, because it is 2 theta, so it is actually cos a theta, so integration will be sin a theta by a, so it is sin 2 theta by 2, limit will be from 0 to pi. So here upper limit pi minus lower limit 0, it will become pi, and sin 2 theta upper limit, if you put upper limit pi here, it will become sin 2 pi, and lower limit will make it sin 0, and we know that sin 0 is also 0 and sin 2 pi is also 0, both will have value 0, so it will be 0 minus 0, this whole term will become 0, only this term will remain pi minus 0 and will become pi, and here we have pi, so both pi will get cancelled, and this will become im square by 4 to the power 1 by 2, so it will be root of im square by 4, and when it will come out of the root, it will become im by 2. This is IRMS, and the unit will be amperes, because it is current, the unit will be ampere. Now coming to VRMS, RMS value of voltage, the thing remains same, the nature of derivation will remain same as of IRMS. First we have to take the square, so we have taken V square, then we have to take its mean, so we have added all the values from 0 to 2 pi and divided by 2 pi, so this is mean, adding all values within range 0 to 2 pi divided by the total range 2 pi, so this is actually mean, and finally the root of it, so this will give you VRMS. And now we know that the V will have the same equation as we had previously. That relation was this relation, VO equals to VM sin theta for limit 0 to pi, and it is 0 for pi to 2 pi, so this equation will remain same. We know that VO has two different nature, it has sinusoidal nature for this range and 0 for remaining range, so we have to divide the integration in two parts. First range from 0 to pi v square d theta, another range from pi to 2 pi v square d theta, because we know that the value of v for 0 to pi is different and from pi to 2 pi is different, and for pi to 2 pi the value is 0, so this whole integration will become 0. Now on left hand side, this should be within a root, because it has to be in under root, so I am doing it. So I did this, I have substituted this 1 by 2 pi within the root, so now this equation is now more clear. This 1 upon 2 pi will be within the root, and this integration will become in two parts, 0 to pi and 0 to pi. The second part will become 0, because for this range value of v is 0, and for this range 0 to pi the value of v is actually Vm sin theta, so square of that v will become Vm square sin square theta, and this Vm, because it is constant, it should be taken out of the integration, so it has taken out from the integration, and here we have integration of sin square theta d theta, and we know that we cannot solve the integration unless we remove the square sign from here, so equivalent of it, the value of sin square theta is actually 1 minus cos 2 theta by 2, and from this we can take 2 on left hand side to make it 4, and this bracket 1 minus cos 2 theta, it has minus sign, so in this integration will be split in two parts. First will be integration 0 to pi of this 1 with respect to theta, and second will be 0 to pi cos 2 theta with respect to d theta. So this is the integration. It has split it in two parts, and integration of 1 with respect to theta is theta with limits 0 to pi, and integration of cos 2 theta is sin 2 theta by 2 with range from 0 to pi, and this whole will go under root. So root has, we have taken to the power 1 by 2 to remove this root. Now this upper limit minus lower limit will give you pi minus 0, and here upper limit will give you sin 2 pi, sin 2 theta, and theta will be pi for upper limit, so it is sin 2 pi, and the value of sin 2 pi is 0, so here we have 0. And when you put lower limit 0, so sin 0 will give you 0, so 0 minus 0, this whole term will become 0, and on this side you will remain with pi, and we have pi in this denominator also, so this 2 pi will get cancelled, and we'll get Vm square by 4 within the root. Vm square by 4 within the root. This pi will get cancelled, and when you take out Vm by 4 out of the root, when you remove it, you will get Vm by 2, and IRMS was Im by 2, Vrms is Vm by 2. Things remain same, just you have to replace I with V to get the value of Vrms. So wherever we write voltage, we have to write unit of it, volts. Now AC power supplied to the rectifier circuit. So this will be actually I square R. The formula of power is I square R. So AC power will have IRMS square, and DC power will have IDC square. This is AC power supplied to the rectifier, and this is AC power DC power supplied to the load. So DC power will have IDC square into RL. AC power will have IRMS square. So IRMS will be for AC, and IDC will remain for DC power. For DC we will have IDC, and for AC we will have IRMS. And regarding this bracket of resistances, so when you look at when you see the figure from this side left of rectifier, you will see three resistances. So because this is written here, AC power supplied to the rectifier, so power supplied to the rectifier means it will be from left side of rectifier. So when you see from the left side means from the transformer side, so you will see three resistances, RS, RF and RL. So when you see from the transformer side, you will see three resistances. So this is AC power, and AC will be available at transformer side. So from transformer side you will see three resistances, so you can see three resistance in the equation. And in DC, when you see from output of rectifier, because power supplied to the load and the power given to the load, it is given by the output of rectifier. So if you see from output of rectifier, you will see only RL, you will not see RS and RF. So when you see from the output of rectifier to the load, you will see only resistance RL, so you can see only RL here. But this will not do too much change, because the value of RS and RF, it is very much less as compared to RL, so they can be neglected. So if you neglect this, you will get the same relation, PS equals to IRMS square into RL. So RF can also be neglected in comparison with RL. So both equation will remain with RL. The thing that is different is IRMS square is there in AC power, and IDC square is there in DC power, and the value of IDC is Im by pi, and the value of IRMS is Im by 2. This is the difference. And we know that the output of rectifier is DC, so it is PDC, and input of rectifier is AC, so it is PAC. So when we want to find efficiency of rectifier, we have to take the ratio of output power to the input power. So output power is DC power to the input power is AC power, So ratio of output power PDC upon PSC will give you efficiency of rectifier. This is actually efficiency of rectifier. Efficiency of half a rectifier. It is output of rectifier, DC output of rectifier divided by AC output of rectifier. So whatever formula we got here, we have to take its ratio, Im by pi square into RL, this is DC power, and Im by 2 square into RF plus RL, this is AC power. But here RL is very much less than RL, RF is very much less than RL, so we can neglect RF in comparison with RL. So it will be RL by RL, they will get cancelled, and you will remain with pi 4 upon pi square, and the ratio will give you the efficiency as 0.406. So percent efficiency will be 40.6%. This is important question for as in the sense of examination. So you may be asked in examination to show that the efficiency of half a rectifier is 40 or below 50. So you may be asked in question examination that you have to show the efficiency of half a rectifier below 50 or approximately 40. Now coming to ripple factor. Ripple factor, actually it is a factor that defines the variation or ripple in the output of rectifier. This is also known as form factor. It can be asked to you to explain or derive for form factor or ripple factor. It is denoted by small r. It is not a standard denotation notation that you may find different notation in different books. I am taking small r for ripple factor. Actually ripple factor, it is a factor that defines you the variation in output signal. So variation is actually AC component and constant nature is actually DC component. So AC component upon DC component give you ripple factor. So it can be found out by using variation in current divided by DC component, or variation or AC component of voltage divided by DC component. So it is actually the ratio of AC component to its DC component. Either it can be voltage, it can be current. So if you take voltage, you have to divide it by voltage. If you take current, you have to divide it by current. This I dash RMS, actually it is the RMS value of output of rectifier. IRMS that we found lastly, this VRMS that we got here, it is actually VRMS at the secondary of transformer, means at the input of rectifier. Here this VRMS is at the output of rectifier. So to differentiate between these two VRMS values, I am putting here dash sign. This dash indicates that it is at the output of rectifier. So RMS value of AC component of output waveform. This is AC component of output waveform, and this is VDC is the DC component of output waveform. So these two parameters are of output. This is AC component. AC component, it is calculated using VRMS, and DC component is calculated using VDC. So ratio of AC component upon DC component is actually ripple factor. Here all the things are defined. Now we know that at the output we have a voltage that has a DC component and a AC component, but when we get AC at the output side, we generally get harmonics from that AC. So wherever we have AC component at the output side, we may have harmonics from that component. Harmonics, you may know that every AC signal, when it passes through some electronic device, so when it comes out from the device, from the output side, it comes out with the harmonics of it. So the frequency that you have applied at the input of that electronic device will be called as fundamental frequency, and at the output side you will have fundamental frequency component as well as its higher harmonics. So I have taken this figure from net. This is actually showing you harmonics. This green signal is a signal that is having fundamental frequency, means when you apply AC signal or signal having frequency f to the electronic device, then at the output side you will get the same signal with frequency f, but along with that you will get another signal with that will be called a second harmonic. it will have amplitude lesser than the amplitude of this. You can see the amplitude, it is quite lesser as compared to this amplitude of fundamental frequency, but amplitude is less but frequency of this signal is quite high. This is actually the time period. With the time period of fundamental frequency, it has 1, 2 and 3 signals within the time period. The frequency is 3 times larger than the frequency of this fundamental signal. The fundamental signal has a frequency f, and the frequency of this second harmonic will have frequency 3 times f, and likewise this is third harmonic, it will have 1, 2, 3, 4, 5 times larger frequency. So but amplitude is again very less. So in this way you will have third harmonic, then likewise fourth, fifth, sixth, seventh higher harmonics are also there, that can be neglected because their amplitude is very less. So at the output side you will have a signal that will be having fundamental frequency, and along with that you will have higher harmonics. But in case of rectifier, you will have a DC component that will be known as VDC, and the AC component which will have fundamental component plus the second harmonic, third and fourth, and likewise. So all the harmonics with fundamental will be labeled as V dash. This V dash will give you will show you AC component with fundamental plus all the harmonics, and this VDC is the DC component, and combination of these two will be the output of rectifier. So we can take this V dash on left hand side to get this equation. Now we know that VDC is Vm by pi. Actually you see here V dash is actually the AC component at the output of rectifier, and VDC is the DC component. So to get ripple factor we have to take the ratio of V dash upon VDC, not V dash, actually V dash RMS upon VDC. So VDC is already available here, just we need to find V dash RMS from this V dash. So we have to find V dash RMS using this V dash. So using V dash we can find V RMS by doing the same thing, squaring it, V dash square, then taking its mean 0 to t dt divided by t. This is mean, and taking its root, this is V dash RMS of this V dash. So we have taken RMS of it. Now why we have taken t instead of any range pi or 2 pi? Because this is actually composite signal. V dash is a composite signal, it has a signal with time. This we have this, it has a fundamental signal, it will have time period t, let it be 2 pi, and this signal will have time period very less than t, it is actually t by 3 here, so it will be very less than 2 pi. So we cannot integrate a composite signal just with same range. If we are able to separate the first fundamental signal, then we can integrate it from 0 to 2 pi. If we separate the another signal, then we can integrate from 0 to let it be pi by 2, so and third will be pi by 4 likewise. But we cannot separate the composite signal, so we have to take the integration range of integration as 0 to t generalized form. So we have taken it as 0 to t and divided by t. Instead of taking a range, finite range 0 to pi or 0 to 2 pi, we have taken generalized, because we have here composite signal, and each signal within the signal composite signal, each signal within composite signal has different time periods. So we have to generalize it, we cannot take it finite value, we have to generalize it because of we have composite signal. This V dash we have as V minus VDC, so we can put here V minus VDC. This is A minus B whole square, it can be expanded as A square minus 2B plus B square. This A square is V square, minus 2AB is minus 2 VDC V, and B square is VDC square. Now this bracket can be splitted, this integration can be splitted for this bracket as integration of this first part V square, integration of second part V, and third part VDC. And VDC is actually constant or a DC component. DC component is average or mean or constant value. Since it is constant, it can be taken out of the integration, so integration will be 1 upon t, here it will remain 1, so it will be 1 dt. integration will be actually it will be 1 of dt. Here integration will be v square dt, because v square, v is variable, it is changing from 0 to t, so it will v square dt, 1 by t v square dt. Second is actually 2 vdc, because vdc is constant, so it has taken out of the integration 0 to that is 2 vdc, and 1 by t it is as it is, integration 0 to t or and v dt. So from this integration, this 1 by t is already outside of the integration, this 2 into vdc is also taken out of the integration, so 2 vdc into 1 by t, it is integration 0 to t v dt. And the third one is like this, vdc square is constant, so it has taken out of the integration, and integration of 1 dt. The first integration is appearing as vrms, because vrms is actually squaring, then taking mean, and then taking root of it, so this is vrms, but here root is not visible, so I can do like this. It is vrms. So this actually, if I add here root, then it will be root mean square vrms, but here we don't have a root term, because this root is complete from this for this 3 terms. The for first term we don't have a separate root, so just to explain, I have substituted here root, but I am undoing it. Now this is actually, this first term, it is appearing like vrms, so I have written here vrms, but here root is not present, so it should be vrms square. The second term, 1 by t integration 0 to t v dt, it is appearing as vdc, average, adding all values of v from 0 to t divided by t, it is average. It is average is written as vdc, so 2 vdc is there, but this integration will become equal to vdc. So here we will be having 2 vdc into vdc. And third is vdc square, and integration of 1, if you add 1 from 0 to t, if you divide it by t, you will get equal to 1, because integration of 1 is small t, and upper limit will be capital T, lower limit will be 0, the upper limit t minus 0 will be t, and divide by t, t by t will get cancelled, you will get 1. So in result of this, integration will turn to be 1. Result of this integration will become equal to 1. So we can put the result here, this integration will become equal to vrms square, so we will get vrms square 1 by t, this integration will become equals to vrms square. So here we have vrms square, here we have 2 vdc, 2 vdc will remain as it is, and this integration 1 by t integration v dt will become equal to vdc, so we will be having 2 vdc here. And third, it is vdc square into 1, so vrms square minus 2 vdc into vdc square, and this is vdc square, so it is minus 2 vdc square plus vdc square, minus 2 plus 1 is minus 1, this will be equal to minus vdc square. So this equation is appearing as v square vrms square minus vdc square. Now squaring this equation, you will get v dash rms square equal to vrms square minus vdc square, and dividing the whole equation by vdc square, you will get an equation like this, v dash rms square divided by vdc square equal to v rms square by vdc square minus 1, because dividing vdc square by vdc square will give you 1. This v dash rms upon vdc is actually rms value, v dash rms upon vdc is actually equal to r, it will give you r, but here we have a square of it, so we have to take under root on both the sides, so you will get vrms upon vdc equal to under root of this term, and this term under the root. So this will be equal to ripple factor. So ripple factor is given by under root of vrms square divided by vdc square minus 1, and we know that for half a rectifier vrms is vm by 2 and vdc is vm by pi. So if you put this here, the VM will get cancelled and you will get ripple factor as 1.21. This is also very important question. You may be asked in examination to prove that the ripple factor for half a rectifier is 1.21. So remember, this is an important question. Now starting the next topic, peak inverse voltage. This peak inverse voltage, actually it means the maximum peak is the maximum, it means maximum, inverse is the reverse voltage, the maximum reverse voltage. Peak inverse voltage, it is actually maximum reverse voltage that comes across diode in this case, or that a diode can handle safely without going into breakdown region. That is called as peak inverse voltage. But in this case, the peak inverse voltage is the maximum reverse voltage that appears across diode. So when positive cycle will come at the input side, the upper side of primary will become positive, and simultaneously the upper side of secondary will also become positive. So when this will become positive, diode will become forward bias. In that case, the voltage that is appearing across diode is forward voltage. But in case of peak inverse voltage, reverse voltage must come. So this will, you can experience this in case in second case, means when you receive negative cycle. So second half cycle is the negative cycle. So for second half cycle, the lower side of secondary and primary both will become positive and upper will become negative. In that case, diode will become reverse bias. So when diode is reverse bias, no current will flow in the closed loop. When diode is reverse bias, no current will flow in the closed loop, because the lower is positive, upper is negative. The current will try to rotate in anti-clockwise direction. So and it will try to enter from cathode of diode, but that will not permit. The diode will not permit to enter the current from its cathode side. So no current will flow in this direction. So if current is 0, the drop across RL will also be 0, because using Ohm's law, VO, output voltage, can be found out as V equals to I into RL. VO equals to current into RL. Because current is 0, so VO will also be 0. So no drop will occur across RL. So complete voltage that is appearing in the secondary side, it will come across this RF. It will come across the diode, and we know that we actually used to label the peak voltage as VM, the peak of voltage as VM. So I brought this figure here. We generally label this height as VM. This is the maximum voltage at the output of rectifier. This is maximum voltage at the input of rectifier. This is also labeled as Vmax. This is also labeled as Vmax or Vpeak or VM. We can label it by any name. Here in this figure, it is labeled as Vpeak and positive, and Vpeak negative. At the output side, it is labeled as Vpeak, and this Vpeak is same as this Vpeak, because rectifier is not made to change the high voltage level. It is just to remove the AC ripple. So it will keep the Vpeak as it is at the output side. So coming to the figure, so the peak voltage at that secondary of transformer, this peak voltage will be VM. That maximum voltage that will appear across RF is actually VM. The reverse voltage, the maximum reverse voltage that appears across RF in reverse bias, that will be equal to VM, because the maximum voltage of secondary is VM. So this whole voltage will come across RF, because no voltage will drop across RL, as current value is 0. Using Ohm's law, V equals to IR. If I equals to 0, V will also be 0. If voltage drop is 0, so complete voltage will get drop across RF. So the maximum voltage that is coming across the diode is the voltage at secondary, and that is VM. So in the case of a half a rectifier, peak inverse voltage of half a rectifier, it is actually VM. Now next is transformer utilization factor. It is a factor that actually shows you the utilization of transformer. So if transformer has a power available as 50 watts, if a transformer is made to give you power of 50 watts, then if you utilize complete power 50 watts, then utilization will become 100%. So the factor will become equal to 1. Transformer utilization factor, it shows you the utilization of use of transformer. If you use it completely, it means that whatever power that is available at the transformer, you have used all the power. So the power that is available at the transformer is the power at its secondary, and that is labeled as, that is known as PAC rated. This PAC rated is the power that is available at the transformer secondary. And if you use the power is if the power that is used at the output of rectifier is PDC, so the same power will be consumed from the transformer, so the utilization will become PDC upon PAC. So understanding this by using this figure, if load is consuming a power PDC, then rectifier will consume the same power PDC from the input side. Simultaneously, the transformer will consume the same power from the AC input cycle, because transformer is made to just transfer the power. So it just take the power from the input side and it transfers the power to the output side. It just transfer the power. If power utilization at the secondary is 10 watts, then the power utilization of input side will also be 10 watt if losses are neglected. So if power used at the load side is PDC, then the power that is used by the rectifier from the secondary side will also be equal to PDC, and the power that will be consumed by transformer from AC input will also be equal to PDC, because the same power is going to transfer from input to output side. But the capacity of transformer is made to transfer power PAC rated. It is made to transfer power up to PAC rated. So assume a power PAC rated as, let the power available at the transformer secondary be 10 watts, and if you use only 5 watt, then TUF will become 1 by 2, that is 0.5. So the power, if power consumption of this load is 5 watt, and if power available at the secondary of transformer is 10 watt, then utilization become half, 0.5. So this is actually just an example to make you understand this thing, that available power is different thing and the power used is different thing. The power used by rectifier from the secondary is different, and the power available at the transformer is different. The power available is the maximum capacity of transformer that it can transfer up to PAC rated, but the power used by rectifier is the same power consumed by the load. So you can apply more load to use the power available at the transformer, but you cannot use power more than that is the capacity of transformer. You cannot use power more than the capacity of transformer. If you do that, transformer will heat up. So you can define this as the ratio of power delivered to the load, means power consumed by the load, to the AC rating of transformer, means the power AC power available at the transformer. So this can be written as formula PDC upon PAC. PDC is the power consumed by the load, or power taken by the load, and PAC is the power available at the secondary of transformer. And PDC, we know this upper term, PDC is IDC square RL. So and IDC is actually Im by pi, so this will become Im square upon pi square into RL. This PAC rated is actually the power at the secondary of transformer, and we know that this is AC signal, complete sinusoidal signal, so we have to take RMS value of voltage and current. So RMS value of voltage will be VRMS, and RMS value of current will be IRMS. But the thing is that the VRMS is actually equal to VM by root 2, and IRMS is equal to Im by 2. You have to understand this thing. The power that is transferred to the output side is actually a part of voltage and current. Power is actually equal to V into I, voltage into current. So when you see the waveform of it, you can understand this by looking at waveform. So this is the waveform of the output signal, and this is the waveform of input signal. So at the input means at the secondary of transformer. So at the secondary of transformer, the nature of voltage will be like this, input voltage, and at the RL side, the VO, output voltage, will be having this nature. So at the output side, when voltage will increase, current will also increase because of Ohm's law, and when current voltage becomes zero, current will be also zero because of Ohm's law. So at the output side, the nature of voltage and the nature of current will remain identical. When voltage will increase, current will also increase. So current will also follow the nature of voltage at the output side. When voltage will become zero, current will also become zero at the output side. So current is the thing which actually flows, and voltage is the potential difference. So when potential difference will occur across RL, there will be flow of current, and when potential difference becomes zero, current will also become zero. So this is the current, and the same current is flowing in the secondary side also, because this is closed loop. So as it is closed loop, the same current will flow through RL as well as through the secondary of transformer. So when current will flow in RL, the current will also flow in secondary, current will also flow in diode. But when there will be no current in RL, so if no current is flowing through RL, so no current will be flowing through secondary, and no current will be flowing through RF. So at the input side, we will have the nature of current same as the current of output side, because the loop is same. As the loop is same current will flow throughout the loop, and the output is also within this loop, and input is also within this loop. So output and input both are with the same loop. So if output current will become zero for this pi to 2 pi range, the input current will also be zero. So nature of current at the input side will be like this. So VRMS for IRMS for the current, RMS value of current at the secondary will be same as the RMS value of current at the output side. This is the case. So RMS value for half wave rectified signal, is actually Im by 2. So RMS value of current at this side will also become Im by 2, because current is same at output and in. As the current is same for output and input, RMS value of current will also be same for output and input. For output, RMS value of current is Im by 2. So input at the input side, it will also be same Im by 2. This will be Im by 2. IRMS will be equals to Im by 2. But the voltage at this input side is full sinusoidal. So we know that it is standard signal for sine wave, complete sine wave from 0 to 2 pi. The RMS value is actually Vm by root 2. This is standard thing that we can derive from if we take RMS value and with range from 0 to 2 pi, and that will be equals to Vm square sine square theta from 0 to 2 pi divided by 2 pi, and taking root of that, we can have value equal to Vm by root 2. So Vrms for complete cycle is Vm by root 2, and IRMS for half cycle is Im by 2, because at the input side we have half cycle, because the loop is same. Or at the output side we have half cycle of current, at the input side we will have half cycle of current, and IRMS will be equals to Im by 2. So if these two things are available, then we can put Vrms and IRMS, because this PAC rated is the secondary of transformer, power available at secondary of transformer. This can be Vrms is Vm by root 2, IRMS is Im by 2. So by putting this, we have Vm Im by 2 root 2. So if PC power, rated power is available, and if DC this is also available, then we can put this in equation of TUF, PDC upon PAC rated. So PDC is put it here as Im by pi square RL, and PAC rated is substituted here as Im Vm divided by 2 root 2. Then we can cancel Im from this side, and from this side we will get Im only here. Here we had Im square, and that has cancelled with this Im at denominator side. So only Im will remain in numerator, and this Vm is also available here, and this RL is there. Now we can have this Im as Im equals to Vm by Rs plus Rf plus RL. This is actually already available, already derived at the start of this topic. Im equal to Vm upon Rs plus Rf plus RL. So we can put either at IM side we can put IM equal to VM upon this whole bracket, or at VM side we can put IM into this bracket. So this IM will get cancelled here. Now in the numerator side we have RL, and in the denominator side we have 3 resistances. So we cannot cancel unless we have this RS and RF as 0. So we can make it 0 by comparing with RL. So this RS and RF, it is very less as compared to RL, so they can be neglected easily in comparison with RL. So as soon as you neglect it, you can cancel RL with this RL. This RL can be cancelled, and you will remain with 2 root 2 by pi square, and the value for this, if you solve it in calculator, you will get 0.286. It is quite less value as compared to 1, because the available power, if it is 10 watt, and if you utilize complete power 10 watt, then the utilization is 100%, and 100% value will give you 1. TUF will be 1. 10 watt upon 10 watt will be equal to 1, but here the value is 0.286. It means that using half a rectifier you can utilize only 0.286 of the available power, 0.286 or 28.6% of the available power. If you take percent TUF, this indicates that you can use only 28% of the available power. So this is very bad thing. This is actually disadvantage of half a rectifier. Even if the power, good power is available at the transformer, you can utilize only 28% of the available power. So this comes under the disadvantage of half a rectifier. It has low TUF. It is lesser than 0.5. It has less efficiency, less than 50%. It has large ripple factor, greater than unity. So using TUF you can also find the transformer. If you want to make half a rectifier, if you want to run a load of 1 watt, if you want to run a load of 1 watt using if you want to make a rectifier that should supply 1 watt at the output side, and if you want to use half a rectifier, then you must have a transformer of 3.496 watt. Transformer is this is not actually measured in watt, it is measured in VA. This is actually V rating of transformer, because for AC generally we measure power as VA rating of transformer. The VA rating of transformer must be equal to 3.496. Unless we have this much value, we cannot transfer 1 watt power to the load side, because it only transfers 28%, 28.6% of the power of this 3.4. So this is helpful in designing, this TUF is helpful in designing the rectifier circuit. If you know the utilization of power at the output side, if you know which rectifier you are using, then you can calculate the power that should be available with transformer. So if you purchase a transformer of 3.496 or higher VA rating, then it can easily transfer 1 watt of power to the load side. So this is all about the topic 1.2. This was actually topic 1.2. So thank you for this.